which or we have not seen each other. No? Okay. Now I think um, next week. I think next week um, is probably the schedule of your pre-final exams. I think I was advised by my colleagues that I can probably give a lecture today and then next week. Okay, two topics. Okay, and this will be the basis of your coverage for your exams for the finals, no? Pre-final exams. Okay, so yeah, you just try to agree with your respective teachers when you're going to have your pre-final exam because we were not able to do a lecture for the last three meetings. Okay, so I think for today we can probably discuss in situ stresses. Okay, and then next week we can probably discuss settlements. No? Okay. Okay, so let me just try to share my screen. Okay, so can everyone see my screen now? I'm now sharing my slide. Um, Now, in case you cannot hear me or if you cannot see my screen, please prompt me immediately. No? So I can try to check what's the problem. Okay, so there's nothing here in the chat box, so I presume that everything's all right. Okay, so for today, or sorry, for tonight rather, let's try to discuss a little bit about in situ stresses. Okay, so when you say in situ, that means the stresses that we encounter in the soils on site. Okay, I think in strength of materials, we are familiar with the word stress. Okay, um, I think we define stress simply as the force over the unit area. Okay, so it's the same definition here, no? In uh, geotechnical engineering. That's how we define stress. Okay, only that the areas are quite different. No? Okay. Okay. Now to understand more about these in situ stresses, again, let's try to recall that soils are again multi-phase systems. No? That means we have the solid, the liquid, and the gas phases. Okay. Now, for a given volume of soil, the solid particles are distributed randomly with void spaces in between. Now, these void spaces are again continuous, okay, and are occupied by water and or air. Okay, so if it is water, then that means it's fully saturated. It is if it is just air, then that's fully dry. Okay, and if it is a water and air, then you have a partially um, um, saturated condition. Okay. Now, to analyze problems such as on earth retaining structures, load bearing capacities or soil bearing capacities, settlement of foundations, okay, stability of embankments, and as well as earth slopes. Okay, then we need to know the nature of the distribution of the stresses along a given cross section of the soil profile. Okay, and normally when we prepare, or rather when I prepare geotechnical reports, normally we provide the soil bearing capacities. Okay, normally when we determine the soil bearing capacities, it's a function of either the shear failure, okay, the shear failure of the soil, or the settlement failure. Okay, and then we have criteria for that. Okay, so that means we need to know the settlements, no, in the structures. Okay, so your structure with respect to foundations, okay, it can either fail by shear, okay, where you can see some bulging of the ground on the sides of the foundations, or by settlement. No? The whole structure will move down, okay, yeah, in such a way that you can no longer open your door. Now, to avoid that, then we need to understand these in situ stresses. So let's try to go over this topic quite slowly, okay? Because it's a bit confusing. Huh? The terms are a bit confusing. Okay. Um, Now, to understand the concept of in situ total and effective stress, okay, we can probably consider a saturated soil with no seepage. Okay, let's consider no seepage first. And then let's consider stresses in saturated soil, this time with some seepage. Okay. Yeah. Now, with this concept, one can try to calculate the increase in the soil stresses with various loading conditions commonly encountered in the field, such as the live load surcharge. When you say live load surcharge in the field, this can be people or moving objects. Okay. Yeah. And then we also have these embankment loading conditions, no? And so on and so forth. Okay. Later, I think what is important for this topic is we try to understand these two terms, no? At least these two terms, no? The total stress and the effective stress. No? So for the remaining three topics, or rather the remaining four topics, including this one, okay, we will be talking uh, about total and effective stresses. Okay, so let's try to understand these two terms. Okay, what's the difference between total and effective stress? Okay, so we have here a figure. Okay, this one here. If you have your book with you, it's just the same figure. I just copied it here in the slide. But if you have your book, you can also look at your book. Okay, I hope it's still the same figure number. That's a figure 9.1 in your book. Okay. So here in figure A, this one here is figure A. Yeah. Mm, So here we try to consider the effective stress consideration for a saturated soil. Take note that it's a saturated soil. That means it's fully occupied by water, okay, in all the voids. Okay, but in this case there is no seepage. Okay, so here you can see in figure A, you have here the solid particles. Okay, the solid particles. And then you have here the voids, okay, with some water on top, okay, at a height of h, okay. And then the voids here are all occupied by water. So that means we have pore water. Okay, the pores are all occupied by water. And then you have the solid particles. Okay. So later, we want to know what is the effective stress at point A, for example, okay, wherein a point A has a height of h sub a. If you can see my cursor, I hope you can see my cursor. At a height of h sub a from the top of the water level. And then h here is the height of the water column from the top of the water until the top of the solid particles. Then here we can consider a cross-sectional area of a bar. That's the cross-sectional area for the whole solid particles. Okay. So just to go back here, let's just try to read through the text. Okay, I just again took this from the book. Okay, if you don't mind. Okay, so that figure, okay, or rather the figure 9.1a, okay, shows a column of saturated soil mass with no seepage of water in any direction. Okay, so later on we will have seepage of water. Okay? For the moment, let's not try to consider seepage. Okay? There's no movement of water in any direction. Now at point A, okay, so we go back here again at any point. Okay, this the point maybe here or here or here, but a certain moment, let's consider the point A somewhere here. Okay. Now at that point A, um, so to calculate the total stress, okay, at the elevation of point A, now the total stress there can be obtained from the saturated unit weight of the soil as well as the unit weight of water above it in such a way that the total stress as symbolized by the Greek symbol sigma, okay, sigma, okay, is equal to capital H, where H is the height of water table from the top of the soil column. So this one. This is the H. That's the height of the water table from the top of the soil column. This is your soil column with a cross-sectional area A bar. Okay. So we have here now that's H times the unit weight of water. Okay. So that's unit weight of water is, let's say, 9.81 kilonewtons per cubic meter multiplied by the height in meters. So this one gives you a unit of pressure. Okay, that's kilonewtons per square meter, for example, which is the same unit for stress. Okay, okay. Then plus you have here. Okay, so that's this one. H times the unit weight of water. Okay. And then we have also here, that's H sub A minus H. What's that one? That's H sub A minus H minus H. Okay, that's actually this height. No? It's actually this height. Then multiply that by the saturated unit weight because we presume here that everything is saturated, considering that there's a column of water on top of it. So that means all this water is seeping through all the voids, filling it up with water in such a way that we have a fully saturated um, uh, soil column. Okay. Now, for example, if this is dry, if there's no water table here, everything's dry. Then we have here the dry unit weight. Okay, so then you can multiply here instead of the saturated unit weight, then you can multiply the dry unit weight. Okay, so again, if you try to recall, we have the saturated unit weight, the moist unit weight or the total unit weight, and the dry unit weight. No? For example, in the geotechnical reports that we prepare, we normally present the dry unit weight. Okay. Okay. Looking at this equation 9.1, okay, again, if you have your book, just try to refer to your book if you're more comfortable looking at your book. Okay. Now, this equation 9.1, okay, can now be considered the total stress. So just depending on the ground condition, if you have a moist unit weight or saturated unit weight or dry unit weight, then that's the parameter that you multiply here. Okay? Now, in this equation, we can see that the total stress, sigma, okay, can be divided into two parts. Okay? So this can be the first part, and then this one here is the second part. Now, the first part here, this is actually the portion of um, the portion that is carried by the water in the continuous void spaces. Okay. Now, this portion acts with equal intensity in all directions. Okay, so that's basically this one here, no? The poor water. Okay, okay. Then the rest of the total stress is now being carried by the soil solids. Okay, at their points of contact. Okay, so if we look at this figure here, at point A, okay, if you try to um, pass through a line here, a wavy line, because yeah, it's not the points of contact between particle to particle is not straight. Okay, so it's a wavy line. Okay, so here you have now your points. If you can see my cursor, these are now your points of contact. No? Okay, so for example, if we enlarge or if we try to extract this part here, this is now your wavy line, then these are now your points of contact, no? In such a way that there's now a force P sub 1, P sub 2, P sub 3, and P sub 4. Okay. Now, you notice here that the forces of contact, depending on how the particle to particle is being uh, connected to each other, then the direction of the force, okay, is not vertical. Okay, they are, some of it may be vertical, but some of it may be at an inclined direction. Okay. Now, if we consider the vertical components, okay, if I consider now the vertical component of this force, the vertical component of this force, this is probably vertical already. Okay? And then this one is, yeah, we can also consider the vertical component of this force. Okay? Then the sum of the vertical components of the forces developed at the points of contact of the solid particles per unit cross-sectional area of the soil mass is now what we call the effective stress. Okay, so that means if I consider now, yeah, this one, the vertical component of P sub 1 over A sub 1, okay, yeah. So A sub 1 then corresponds to the area of contact um, in relation to the vertical component of P sub 1. Okay. Then so on, A sub 2. This is now the area of contact of the vertical component of P sub 2, then as well as A sub 3, and then A sub 4. Okay, because not all areas or not all areas of the solid particle are basically in contact with another particle. So only a minor part. which is being represented by this small a terms. Okay. Then again, take note that for the whole soil mass, we try to consider a cross-sectional area of a bar. Okay. Okay. So I think here we now have mentioned two stresses. Okay, you have the total stress and the effective stress. Okay, so let's now try to have the relationship or the basic relationship between the total stress and the effective stress. Okay, now later on, if you want to proceed to geotechnical engineering, understanding these two terms are very important, or is very important. Okay, because otherwise, if you mistake the effective stress for the total stress, then for sure your structure will fail. Okay, it will either settle or it will either lean, just like the leaning tower of pizza in Italy. Okay, okay, that is actually a failure of the effective stress. Okay, so let's just go to this text here. Okay, just didn't change anything from the book because I don't want to miss anything. Okay, so again, going back to the effective stress. Okay, now the effective stress can be seen again by drawing a wavy line, a dash a. Okay, so basically that's this one here. Okay, yeah. Okay. So we draw a wavy line through the point A, okay, that passes only through the points of contact of the solid particles. So again, yeah, we have here the points of contact. Okay, we're just trying to review. Yeah. Okay, so if we now have these P terms, okay, to be the forces that act at the points of contact of the soil particles, okay, which is yeah, which is shown here. Okay, then the sum of the vertical components, okay, of all such forces over the unit cross-sectional area is now then defined as the effective stress, okay, or that's now sigma prime. Okay, wherein sigma prime is now equal to the vertical component of p sub 1 plus the vertical component of p sub 2 plus the vertical component of p sub 3 and so on and so forth until you reach the end, uh, the vertical component of p sub n or the end particle for the end particle. Okay. So that sum divide that by the cross-sectional area a bar, okay, will then give you now the effective stress. Okay. Now, so the cross-sectional area, okay, the cross-sectional area occupied by the solid to solid contacts, okay, let's call it A sub S, okay, is then equal to A sub 1, A sub 2, A sub 3, A sub 4, and so on and so forth until you reach A sub n for the end particle. Okay. So if you sum up all those small areas, then that will give us your A sub S. Okay. So that's the space occupied by the solid to solid contact. Okay. So that means the space occupied by water will now then be equal to um, this A sub bar, sorry, A bar minus A sub S. Okay, so that's uh, this one. Huh? Okay. So we we can now write or rewrite uh, the total stress sigma is now um, U times the space occupied by water, okay? Where U is equal to the pore water pressure, okay? The pore water pressure. Okay, in hydraulics, you have been discussing water pressures, okay, or hydraulic pressures. Yeah. So it's the same concept here, only that we are talking about pore water pressure. Okay, because in unsaturated soil mechanics, there's also what you call as pore air pressure. Okay, in such a way that the difference between the pore air pressure and the pore water pressure is what we call as the matrix suction in unsaturated soil mechanics. But for the moment, here in our subject, let's not deal yet with the pore air pressure because we are assuming that our soil column is fully saturated. That means you only have pore water. There's no pore air. Okay. So by definition, the pore water pressure, or that's basically the hydrostatic pressure at A, okay, that's the hydrostatic pressure at A is now equal to uh, that's equal to the unit weight of water times H sub A. No? Okay. Yeah. So that's this one. No? Okay. So that's the unit weight of water times H sub A. No? Okay. That's your pool water pressure at point A. Okay. Okay. So just try not to be confused because if I multiply the unit weight of water to the height H sub A, that gives me the pore water pressure at point A. Okay? But if I multiply the unit weight of water to this height H, okay, that will give me the total stress. No? So please try not to be confused. Okay. Anyway, later on, we will have some examples where we will try to demonstrate that. Okay, so we now have here the pore water pressure, okay, multiplied by the space occupied by water, which is this one, over the cross-sectional area A bar. Okay, so if we try to simplify this further, then this one will just be one. Okay, and then this one is now A sub S over A bar. No? Again, where A sub S is the cross-sectional area occupied by the solid to solid contact. Okay. So A sub S prime here, okay, is now defined, okay, as the fraction of the unit cross-sectional area of the soil mass occupied by the solid to solid contact. No? That's A sub S over A bar. Okay? So that gives you this equation of here, which is now the general equation for the relationship between the total stress, the effective stress, and the pore water pressure. Okay? Now, the value of A sub S prime is extremely small, okay, and can be neglected for pressure ranges generally encountered in practical problems. Okay, so saying okay, so uh, with that, okay, then that means this one here can just be treated as zero, okay, to be extremely small. So that means you only have one minus zero. That leaves you the pore water pressure. That means we now have here equation 9.4 in your book. Okay, I hope you still have the same numbering. Okay, this is taken from the book that I have. Okay, so that means we now have the basic formula for the relationship between the total stress and the effective stress plus the pore water pressure, such a way that the effective stress is equal to the total stress minus the pore water pressure. Okay? Now, the pore water pressure can also be considered as or can be referred to as the neutral stress, no? In such a way that if this is now the total stress, then the total stress is equal to the effective stress plus the neutral stress. Okay. Now, with this equation, if we try to substitute this equation here for the total stress, if we now substitute this to equation 9.4, okay, this one here, okay. So then this is now your total stress, okay. This is now your total stress. And then to get the effective stress, then we subtract the pore water pressure from the total stress. So that means this one here is the total stress taken from this equation here. Okay. That's now the total stress minus the pore water pressure at point A. Okay. Although it can be any point. Okay. So again, the pore water pressure is defined as this one here. It's the height of the point A from the reference water level, okay, multiplied by the unit weight of water. Okay. So again, please try not to be confused. This one, this unit weight of water multiplied by H, wherein this is now your H, that is needed for the determination of the total stress, while this term here, if you multiply the height H sub A to the unit weight of water, that will give you the pore water pressure. Okay, so please try not to be confused. Okay, so if I just simplify these terms here, okay, then that will give me this one. Okay, if you just can do it yourself, no? Just simplify, then you will arrive at these terms here. So this h sub a minus h is actually h sub a minus h is actually the height of the soil column at point A. Okay? So that's this one. Huh? That's the height of the soil column. Okay. Then this difference here between the saturated unit weight and the unit weight of water can be replaced by gamma prime, okay, where gamma prime is equal to the saturated unit weight minus the unit weight of water. Okay. Then that is now defined as the submerged unit weight of the soil. Okay, or sometimes the boy it's called the buoyant unit weight of the soil. Okay. So in this formula, we can see that the effective stress, okay, at point A is independent. The effective stress at point A is independent on the height of the water column. Okay, so whether the height is 1 meter or 2 meters or 3 meters, the the effective stress rather, the effective stress at point A is just the same. Okay. So to summarize, okay, the effective stress is approximately the force, okay, per
Hey,
unit
what is
area
going on,
carried
guys?
by
Today
the
I'm sharing
soil
with you an
skeleton.
updated video.
We so the particle to particle contact is what you call the soil skeleton. Okay. Now, this effective stress, which we just have defined, okay, in soil mass actually controls the volume change in soils as well as the shear strength in soils. Okay, so later on we will be discussing shear strength. Okay, so I think this will um, after this one, we'll be discussing settlements, then shear strength of the soil, and then yeah, we can probably discuss for our last topic the lateral earth pressure. Okay. Now, increasing the effective stress induces a soil to move into a denser state of packing. Okay. So, if for soil materials, we have a dense state, okay, a very compacted state, okay, and then you also have the loose state. No? Okay. Um, for example, when we try to do backfilling works, you dump the material to be compacted. So before it is compacted, it's still considered as a loose state. Okay, and then after you compact it, then yeah, it's now on a dense state. Okay, so that means the denser the material, the soil material is, the higher is the effective stress. Okay. Okay. So yeah, so just to try to demonstrate. No? Okay. The definitions of total stress, the pore water pressure, and the effective stress. Okay. For example, here you have here a layer of soil. Okay. This is now your soil here. Okay? A layer of soil in a tank where there is no seepage. Okay. So we will know that there's no seepage because here the water levels in the piezometers. No? Let's try to call this as piezometers. Okay. So the water levels here are all the same. No? The same level as the top of the water column. Okay. Yeah. So that means there's no seepage. No? There's no flow either going up or going down. Okay. So in this case, if there is no flow, okay, there is no seepage, then that means we have closed the valve. Okay. There's no supply of water. Okay? So with this, let's try to calculate the total stress at point A, point B, and then point C, for example. Okay? In such a way that the height of the water column is given as h sub 1, and then the height of the soil column is given as h sub 2. Okay? And then point C is located at a distance of Z or Z from the top of the soil column. Now let's consider this as your soil column. Okay. Okay. So to get now the total stress, the pore water pressure, and the effective stress at point A at a depth of h sub 1 from the water level. Okay. So then we can multiply, okay, the height of the water column by the unit weight of water to give the total stress at point A. Now, for the pore water pressure, then yeah, basically it's just the same because I have here just water. Okay, so I still h sub 1 times capital A. Okay? So that means at this point wherein you have just water above it, then the total stress is basically the same as the pore water pressure or the neutral stress. Okay? In such a way that, yeah, if I try to determine now the effective stress at a depth of h sub 1, or that's point A, okay, then the effective stress is just equal to 0 because we subtract the pore water pressure from the total stress. Okay? Now, at point C, okay, at point C, wherein point C is at a depth of h sub 1 plus z, okay, uh, or z, okay. Um, so to determine now the total stress at point C, okay, so we now have h sub 1, okay, times the unit weight of water, okay, plus Z, okay, plus Z times the saturated unit weight of the soil column. No, this one here. And this is now your soil column. Now, for the pore water pressure at point C, okay, I hope everyone can see my cursor. So for the pore water pressure at point C, then it is just equal to H sub 1 plus Z, okay, that's this one here, multiplied by the unit weight of water. Okay. So take note, for the total stress, we did not combine these two terms because we multiply them to the unit weight of water as well as the saturated unit weight of the soil sample. Okay. So then, if I now try to determine the effective stress at this point, then I just simply subtract the pore water pressure from the total stress. So if I subtract these two, then that will now give me this one here. That's Z, this one here, that's Z times the gamma prime. Where again, we define gamma prime to be the saturated unit weight minus the unit weight of water. No? Yan na lang gidiretso-diretso, pagbota. Okay, but you can just simply subtract these two. Again, at point B, okay? So for point B, the total stress there is now equal to H sub 1 times the unit weight of water, okay? Plus, it's just basically the same here, only that instead of using Z at point C, then we now use H sub 2 at point B, okay? The total stress at point B. Okay? Now, for the pore water pressure at point B, it's just equal to H sub 1 plus H sub 2, multiply that by the unit weight of water. Okay? So to determine the effective stress at point B, we just simply subtract the pore water pressure, okay, from the total stress because total stress is equal to the effective stress plus the pore water pressure. Okay? So that will give me H sub 2 times gamma prime. Now basically, it's just the same here, only that at point C, you have a depth of Z, and then at point B, you have the depth of H sub 2 from the top of the soil column. No? Please take note of that. No? It's this reference from the top of the soil column, this one here. It's not the top of the water level. Okay. So, by the way, in this equation here, for the effective stress, there's just a note here that the effective stress, okay, is defined as the sum of the vertical components, okay, of all intergranular contact forces. No? Okay, so I'll go back here. So yeah, so that's this one, huh? The sum of the intergranular forces. No? Okay, so that's this one here. No? Intergranular forces. Okay, so that's the sum of all the vertical components of the intergranular contact forces over a unit gross cross-sectional area. Okay. Now, by definition, okay, by this definition, then it is mostly true for granular soils. Okay, but but in the case of fine grain soils, okay, intergranular contact may not physically be there because for fine grain soils, especially for the clay particles, okay, for clay particles, these are surrounded by tightly held water film. Okay, yeah. So if you try to recall when we were discussing clays, we have the double diffuse layer. Okay. So in a more general sense, then equation 9.3, where is that? Okay. So that's equation 9.3, this one here, okay, this one. And that can be rewritten as uh, this one here. Okay, so if you try to recall, that's basically the effective stress. Okay, sigma prime. Okay, then it can be replaced by um, sigma I sub Ig, no? Where this is now the intergranular stress, okay, intergranular stress, plus this term, which we have defined earlier, minus A bar, A prime, plus R prime, okay, where A prime is the electrical attractive force per unit cross-sectional area of the soil. And then R prime is the electrical repulsive force per unit cross-sectional area of the soil. Now, in the case of granular soils, okay, such as sands and gravels, and then as well as silts and clays of low plasticity, then these two magnitudes here are quite small. Okay? Hence, for all practical purposes, the intergranular stress is just the same as the effective stress, which is approximately equal to the total stress minus the pore water pressure. However, if this term is quite large, then the intergranular stress may no longer be the same as the effective stress. Okay? Now, this situation can be encountered in highly plastic dispersed clay. Okay. Now, many interpretations have been made in the past to distinguish between the intergranular stress and the effective stress. But in any case, the effective stress principle is already an excellent approximation being used in solving engineering problems. At least in my experience, I am not using the word intergranular stress, but rather when we explain um, to our clients, okay, then we always emphasize the effective stress, okay, the effective stress approach. Okay. Now, so far, we have discussed the total stress and the effective stress concepts for a case of soil with no seepage. Now, how about if the water is now seeping? Okay, so there is now a water flow. Okay, so you have now opened the valve, okay, in such a way that water will rise. Okay, then there is now movement of water. Okay, so in that case, the effective stress at any point in a soil mass will differ from that in a static case. Now, it will either increase or decrease depending on the direction of the seepage. Okay. So, for example, we now have here this figure. Okay. So here we now have actually the same tank. Okay. We have the same tank as shown earlier, but we have now opened the valve at the bottom in such a way that there will now be inflow of water. Okay. So then water, okay, sorry. Water will then slowly rise up. Okay. And then this water level will slowly increase. So then you notice now that with the installed piezometers, no, let's try to call them piezometers. With the installed piezometers at different heights, okay, or different depths of the soil column, as you fill in with water, then they are no longer equal. Okay, so then the height of water or the piezometric level at this um, piezometer is now higher at the bottom as compared to um, the piezometer at the top of the soil column. Okay, so which means that if this is now the case, then you now have upward flow. In the case of downward flow, then this one is now higher than the level here. Okay? You can do an experiment of this if you like, just to check. Okay? So with that, then is the difference between this level, okay, and then this level here in the piezometers can be described as a small h. Okay, so between this level and this level is defined as small h, while the difference between this level and this level here um, can be taken as a ratio. No? Okay, so you now have, for example, um, because h small h over h sub 2, which is now the um, your medium for the flow of water. Okay, so that means this one here, h small h over h sub 2 is now what you call your hydraulic gradient. Okay, so that is for um, from point A to point B. But from point A to point C, then you now have these two levels. Okay, these two levels, and then they are rather this one here can now be determined by a ratio and proportion, such a way that um, you now have this difference in height over z. Okay, is now equal to this small h over h sub 2 no? By just ratio and proportion. Okay, by ratio and proportion, then we now have this height is now the hydraulic gradient multiplied by the depth c, simply by ratio and proportion. Okay. So with this condition wherein you now have a flow of water going up, okay, then let's now try to determine the total stress, the pore water pressure, as well as the effective stress. Okay. Now at point A, okay, at point A, um, that the values for the total stress, the pore water pressure, and the effective stress is basically the same at point A for both um, the condition wherein you don't have seepage and for the condition wherein you have seepage either upward or downward. Okay. So at point C, okay, at point C, um, So the total stress is basically the same. Okay, the total stress is basically the same um, for for both scenarios of no seepage and with seepage. Okay, but for the pore water pressure, okay, we now have here yeah the total depth, which is now this one here plus h sub 1 plus z. Okay, so that is now h of 1. Okay, that's h of 1, sorry, h of 1 plus z. Okay, that's h of 1 plus z plus this height, which is now I times z. Because small h over h sub 2 is actually what we define the hydraulic gradient. The hydraulic gradient. Or that's I. No? That's basically I. Okay? So I think for the case where you have seepage, then this is only the added parameter. No? So that can be seen here. In such a way that if we subtract the pore water pressure from the total stress, then we can determine the effective stress. Okay, so that's at point C. Now for point B, actually it's just the same total stress for seepage and no seepage. Okay, but for the pore water pressure, then you now have H sub 1 plus H sub 2 plus small h times the unit weight of water. And so with that, if we subtract the pore water pressure from the total stress, then we now get this parameter here. Okay, so that's now H sub 2 times the submerged unit weight minus the small h, okay, small h uh, times the unit weight of water. Okay, for the effective stress part. Okay. Okay. So basically, this one is already here. Okay. It's just the same. No? We have already demonstrated that. Okay. Um, before I proceed, are there any questions so far? Okay, I hope I am clear. I am trying to be slow as much as possible, okay? So that you don't get lost. Okay. If there are no questions, let me try to proceed. Okay. Okay. So, if we now try to compare figures 9.2D, where's that 9.2D? Uh, yeah, so this one. So if we now try to compare the effective stresses for the case of soil with no seepage, okay? Then if we now try to compare that with this one here, with this effective stress where you now have seepage, okay, then it would show that the effective stress at a point located at a depth z, okay, where's the depth z? So this one here, at depth z, that's point C actually. So the same here at depth z, which is now your point C, okay. So if we now try to compare, if we now try to compare the two, okay, then we can see that the effective stress is being reduced by this amount here. No? Okay? I times Z times the unit weight of water. Okay, so let's see. Yeah, is that correct? So this one here, if I compare, yes. So yeah, we that's being reduced. No? That's being reduced by this term. Okay, and that is due to the upward seepage of the water. Okay, so because of the upward seepage of the water, then the effective stress is being reduced by uh, this amount here. Okay, which is I times Z times the unit weight of water, where I is the hydraulic gradient. Okay. Now, if the rate of seepage and thereby increasing the hydraulic gradient, a limiting condition will be reached in such a way that yeah, the um, the effective stress, okay, will now be equal to zero. Okay. Now, in that case, the hydraulic gradient will now be considered as the critical, no? The critical hydraulic gradient for zero effective stress. In such a way that if you now have zero effective stress, then there can now be some ground failures. No? Okay, ground failures. So then this term here will now be considered as your critical hydraulic gradient. Okay. Now, in such zero effective stress, the soil stability can be lost. Okay, and in such situation, then generally it can be referred to as boiling or a quick condition. Okay, such as when you have quicksand. Okay, so in a quicksand, if you notice, when you step through a quicksand, then you will go down because the soil has already lost its stability. Okay, there's already more water than the sand material. That's why it's called a quicksand. Then you can submerge below it. Okay. Now, boiling or soil boiling, normally it happens um, during an earthquake when the soil layers, specifically the sand layers, will experience what we call as liquefaction. Okay, and then there is what you call then as sand balls. Okay, wherein um, yeah, water will gush out from the ground. Okay. So the critical hydraulic gradient, okay, can be defined as the ratio of the, take note, that's gamma prime, that's the submerged unit weight over the unit weight of water. Okay. Now, for most soils, the value of the critical hydraulic gradient varies from zero point 0.9 to 1.1. Okay. So later on, we will have some examples wherein we have zero effective stresses. Okay. Okay. Um, okay. Now, so far we have discussed soils with no seepage, and then soils with upward seepage. Now, how about if we have the condition wherein you have downward seepage? Okay. Just as just the same as this figure here. So this time, you open the valve. Okay, you open the valve, but this time the inflow or the supply of water is taken from the top. Okay, So there will now be flow of water from the top down to the bottom. And so if that happens, then the water levels at the three piezometers, for example, then they will have this shape. No? Okay. So that means at point A, you have a higher piezometric level as compared now to point B, where you now have a lower piezometric level because the flow is now downward. Okay. So again, the difference between these two levels is what we call as a small h. And then the difference between these two levels is now given by the hydraulic gradient multiplied by the depth C. Okay. Okay. So again, to determine the total stress, the pore water pressure, and the effective stresses. Okay. So again, at point A, wherein the water is just above it. Okay, so there's no change. It's just the same. Okay, just the same at point A. But at point B, well, again, for the total stress, it's just basically the same. Nothing happens. Okay. Um, but for the pore water pressure, okay, for the pore water pressure, you now have H sub 1 plus Z minus, okay, that's a minus um, this one here, or minus this term, okay, minus this term. Okay, so that is for point C. Okay, so that's rather H sub 1 plus Z minus this height. Okay, sorry, yeah, this height here will now give you the height of the pore water pressure multiplied by the unit weight of water. Okay. Um, Earlier we have their plus. Now, if you recall, this one is plus because you now have h of 1 plus z plus this one here. So that's plus. Okay. So this total height from this level to this level at point C will now give you the pore water pressure at that point. Okay. Okay. So again, if we subtract the pore water pressure from the total stress, then that will now give me this term here. Okay. So at point B, for the total stress, it's just basically the same for the other conditions. Okay. But for the pore water pressure, we notice that here you added H because that is H sub 1 plus H sub 2 plus small h. No? Okay. Multiplied by the unit weight of water will give you the pore water pressure. But in the downward direction, okay, um, then you now have h sub 1 plus h sub 2 minus the small h. That will now give you this depth until point B to give you the pore water pressure. Then again, by subtracting the pore water pressure from the total stress, will now give me this term here. Okay. Okay. Now, so far we have seen the effect of seepage on the stresses, no? As well as the pore water pressure, which can either increase or decrease the effective stress at a point in a layer of soil. Now, with that, let us now try to express the seepage force per unit volume. Okay, yeah, the seepage force per unit volume. Okay. Now, earlier we have seen a figure with no seepage. Okay. So from there, we can see that the effective stress at a depth C measured from the surface of soil layer in the tank can be given by this one here. Okay, Z times gamma prime, or gamma prime is considered is being called as the submerged unit weight. That's the difference between the saturated unit weight um, uh, and the unit weight of water. Huh? Okay, yeah. So that's this one here. That's your submerged unit weight. So that means that the effective force on an area, okay, um, can now be equal to the effective stress, okay, multiplied by the area. Okay, so effective stress, that's a unit of pressure, that's force over area, multiplied by area will give you an effective force. Okay? So that is for the downward direction. Now again, if there is an upward seepage of water in the vertical direction through the same layer, then the effective force on the area at a depth C can be now given by this equation. Okay, so this is the case of no seepage, while this is the case of where is this? This is for the upward direction. Okay, this one here. That's the upward direction. So that's a minus for an upward direction, and this is now plus for a downward direction. Okay, so that's given by this one. So which means now that if you um, subtract p sub 1 from p sub 2, okay, p sub 1 from p sub 2 will now give you this term here. Huh? That's IC gamma unit weight times the area. Okay? Or that's rather the unit weight of water, not times the area. Okay. Okay. So here we now have the different forces just being summarized into three diagrams. Okay, wherein you now have the force at for this figure. This is now the force. Okay, due to no seepage. Okay, and then here you now have the forces. Okay, due to upward seepage. Okay, yeah, that's this force here minus this seepage force. Okay, then that gives me this one here. Okay, upward seepage. Okay, and then for downward seepage. Okay, then you now have this one here. This is now the force at no seepage. Okay, um, plus the seepage force in the downward direction. So that's why here you have a plus, and then here you have minus, no? Because that's downward and upward. This is plus because they are both downward or the seepage force. Okay. Okay. Now, the volume of the soil contributing to the effective force is now equal to the depth z at any point, okay, below the soil column. Okay? and then that's um, multiplied by the area, okay, the cross-sectional area, okay, so that gives me the volume, okay. So the seepage force per unit volume of soil, okay, is now given by this term here, which is actually equal to this one, okay. Divide that by the volume of soil, okay. If you divide it by the volume of soil, so this one will cancel out, Z and Z, then capital A will cancel out, and you will be left with the hydraulic gradient I multiplied by the unit weight of water. And this is now what we call the force per unit volume. Okay, that's the force per unit volume. That's the seepage force rather per unit volume. uh. In this case, it acts in an upward it acts in an upward direction. Okay. Okay. So yeah. So we can see that upward direction here. This is in the seepage force in the upward direction. Well, this is the seepage force in the downward direction. Okay. Okay. So that means the seepage force per unit volume, either in the upward direction or in the downward direction, is just the same. That's the hydraulic gradient multiplied by the unit weight of water. Now, take note here, this is a consideration of a saturated soil sample, but in unsaturated soil mechanics, since it is not fully saturated, that means the degree of saturation is not 100%. Okay, so then we can multiply this by the specific degree of saturation. Okay, okay, so then we can conclude that the seepage force per unit volume, okay, is equal to the hydraulic gradient I multiplied by the unit weight of water. Okay? And then in an isotropic soils, the force can act in the same direction of the groundwater table. So all this the sand materials below it, okay, um, is saturated, okay, in such a way that it is a saturated unit weight of 19.25 kilonewtons per cubic meter. So the dry sand is about 6 meters deep, while the saturated sand is about 13 meters deep. Okay. Then below the saturated sand, you have a clay material, a saturated clay material. So then, with this soil profile, we are asked to calculate the total stress, the pore water pressure, and the effective stress at points A, B, and C. So let's start off with at point A. So at point A, the total stress or sigma A is now equal to zero because there is nothing on top of it. Okay, so that's zero. The pore water pressure is also zero because there's no there's no water on top of it. And so the pore water pressure, if you subtract these two, then the effective stress will just also be zero. Okay? Now at point B, okay, say at point B here, uh, the total stress will now be equal to 6 times the dry unit weight of the sand. No? That means that's the we call it the overburden, okay? The overburden above point B. So that's basically 6 times the dry unit weight of the dry sand. Okay, so that will give me 6 times 16.5. That gives me 99. But for the poor water pressure at point B, uh, that is uh, that is zero. That is zero because there's no water on top of it. Okay, so that's zero. Okay, so if we now get the effective stress, then the effective stress is just the total stress minus the poor water pressure. So that's 99 minus zero is just 99. Okay? Now at point C, here at this point, okay, so for the total stress, so that's now equal to the same term here. Okay, so that's the total stress contributed by the dry sand plus the total stress contributed by the saturated sand, which is now um, yeah, which is now 13 times the saturated unit weight of the. No, this is supposed to be sand, not clay. This is typo error. Okay, so that's 13 times the saturated unit weight of the sand. Okay, that's 19.25. Okay. So if you multiply this and add, then that will give you this value here. Okay. And then for the poor water pressure at point C, okay. So it's just basically the total height from the top of the soil column down to point C. The 6 plus 13 is 19 meters. Multiply that by the unit weight of water. Okay. Will give us this value here. Okay. So then for the effective stress at point C, we just subtract the pore water pressure from the total stress, and that will give me this value here. That's about 221 kilonewtons per square meter. So I guess we have now solved the problem. Um, Now, considering the same problem, there's a question here. How high should the water table rise so that the effective stress at point C is just 190 kilonewtons per meter. So that means you're trying to lessen the stress, the effective stress between the soil particles. Okay, so from 221 down to 190 kilonewtons per cubic meter. Okay. Now let's assume that the saturated unit weight is the same for both layers. No? Say from at this layer as well as the layer of soil that where the water level will rise. Okay, so let's assume they have the same saturated unit weight. Okay, so in doing that, okay, so let's consider the groundwater table rise to be H, okay, above the present groundwater table. So say from this groundwater table, this will increase by a certain height H. Okay, balimsakan tubig. No? Okay. So the question is how high should that increase in the water level be in such a way that um, the effective stress at sea is just 190 kilonewtons per square meter. Okay. So with that, to compute the total stress now at point C with this condition now, then we now have a 6. Okay. We now have 6 minus, okay, the height h. So that you can just imagine. Please bear with me. You can imagine you now have this height here. Okay. Yeah. You can imagine that there is now water here at this level, for example. So that's a 6 minus that height of water with the new water level. Okay. Um, then I can multiply that. Sorry, my cursor. I can multiply this height here by the dry unit weight. No? So that gives me 6 minus h times the dry unit weight. Okay. Then plus the h times the saturated unit weight of sand. Okay. Because you already have here an increased height. No? So the new water level is already somewhere here. So that one, that's h times the unit weight of water plus 13 times the saturated unit weight. So you now have this 13 plus or times the saturated unit weight. And then for the pore water pressure, okay, so you now have, for the pore water pressure, you now have 13 plus this height here, no, wherein you have an increase in the water level. So then you now have 13 times h. Then you multiply that by the unit weight of water um, to get the pore water pressure. Okay. So the next question is to solve for this h. Okay, to solve for this h in such a way that the effective stress is 990 kilonewtons per square meter. So then to get the effective stress, then we now have the total stress. Okay, you now have the total stress. I hope you can see my cursor. Minus the pore water pressure. Okay, so for the total stress, you just simply substitute this one. That's here. Okay, minus the pore water pressure, which is this one, and then you just substitute it here. So just by rearranging some terms and then group them together, that will now give you these terms here is equal to the effective stress. Okay, at point C. Okay. Okay, so by just substituting the values, so the effective stress at point C is equal to 190 kilonewtons per cubic meter. The unit or the dry unit weight of sand is 16.5, and then the saturated unit weight of sand is 19.25, and then the unit weight of water is 9.81. Okay. So with that, then what the only variable left is h, then we can solve for h to be 4.49 meters. Okay. So that means the increase in water level is now somewhere here. Okay. So that means that the groundwater level should increase by about 4.5 meters, leaving only 1.5 meters, okay, in such a way that the effective stress at point C will decrease from 221 to 190 kilonewtons per meter, okay? So that means the higher the groundwater level, the smaller is yeah, the effective stress. Okay. Okay. Yeah. So let's have here another example. Okay. So you have here a 9 meter thick layer of stiff saturated clay. Okay. So this one here. This is now your stiff saturated clay. Now, by the way, for clays, depending on how or depending on its consistency, it can be soft or it can be very soft, soft, medium stiff, stiff, very stiff, and hard clay. Okay, in the field. Normally, we determine that by doing an SPT, standard penetration test. Okay, getting the N value. Okay. Now, in this problem, the sand below the stiff clay is under what we call as artesian groundwater pressure. Okay. When you say artesian groundwater pressure, that means the ground or the isometric level is above, that's above the top of your aquifer. Okay, so in this case, the saturated sand is our aquifer. Normally, sands and gravels are considered as aquifers in hydrogeological terms. Okay, so here we have the saturated unit weight for the clay material, and then here we have the saturated unit weight for the sand material. Okay, and then you now have here your depth 9 meters for the clay, and then a depth of 3 meters on the sand. Okay, with a piezometric level of 3.6 meters. Okay. So we are now asked to calculate the maximum depth of cut H that can be made in the clay. Okay, in such a way that there will be no side failures, for example, in this saturated clay. Okay. So with that, due to the excavation, no, you can now assume that you have here originally a soil material, and then you excavate it. Okay, you excavate it. Yeah. So because of that excavation, then there will be unloading of the overburden pressure. Okay. So if, for example, if you have this point here, okay, if this point here, if you consider this point here, originally you have some overburden pressure there above that point, but then when you excavate, then that overburden pressure will be released. So we now then let H be the depth at which the point will now start to heave. Okay, this can happen in stiff clays, for example. No? Stiff clays can heave, no? Or bulge. Okay, yeah. The heaving is different from the term expansive source. Also, it will expand. Okay. So in this case, it will heave because of the unloading of the burden, overburden pressure. Okay. So to solve for H, let us consider the stability of the point A at the time. Okay. So at point A, for example, the total stress here is given by 9 minus H. Okay. So where's that? That's 9 minus H. Okay, that gives me this height. Okay, give me the height, that's 9 mm. Multiply that by the saturated unit weight of clay. Okay, that gives me the total stress at point A. Now, for the pore water pressure at point A, for the pore water pressure at point A, so that's equal to 3.6 meters times the unit weight of water. That's this one here. Now, for a heave, okay, for heave to occur, then there is already a loss of the effective stress. Okay, because when there's already heave, then most probably there's already less contact between the particle to particle, no? Because you are now heaving, no? Kumbaga sabihin ni Saya pa magburot siya, no? Action siya burot. Okay? Ang yuta. That's heaving. Okay? Now, for heaving to occur, the effective stress must be zero. Okay? Because there's no longer effective stress if that happens. Just like in quicksand. Now, in quicksand, the effective stress there is also zero. Okay? That's why uh, you will initially float in the quicksand, but you will initially go down, or you will eventually go down, no? Because the effective stress is already zero. So, to get the effective stress, I just simply subtract these two, the pore water pressure from the total stress, which is now this one here. Okay. Uh, but then I will now equate the effective stress to zero. In that way, I can now calculate my height h, which is now a 7.04 meters. Okay. So that means um, I can still cut here a maximum of about approximately 7 meters. I can cut here approximately 7 meters, leaving me about 2 meters, okay, in order for the clay to maintain its stability. Okay, here. So 7 meters is still quite deep. No? In actual construction, we still put there some shoring. No? Okay. Irregardless if the effective stress is zero, automatically for safety purposes in construction, beyond around 1.5 meter depth, we already try to put some shoring protections on the walls. We cannot take such risk. Okay. Um, okay. I think for this problem, for example, it's just this same case. Okay. The same case. Um, so here uh, we have a cut. Okay. So considering the same situation here, you have a cut that is made in a stiff saturated clay, okay, and then underlain by a layer of sand, this one here, wherein this one the depth of cut is about 5 meters, okay, and then the total depth of the stiff saturated clay is about 7 meters, and then the depth of or the thickness of the sand layer is about 2 meters. Okay. But here you have initially some water. Okay. You have here some water. So that means um, if you try to measure the piezometric level, here, if you can put, no, for example, a piezometer here, then the water will rise. Here, in this case, the water has risen to a height of 4.5 meters. So here you have the saturated unit weight of the clay is 19 kilonewtons per cubic meter, whereas the saturated unit weight of sand is about 18 kilonewtons per cubic meter. Okay. Uh, okay. So the question now is what should be the height of the water? This one here, H, in the cut, okay, in this cut, so that the stability of the saturated clay is not lost. Okay, so then we are asked to determine this height. So what should be the maximum height of this water? Okay, for example, if you want to pour water here, what should be the height of this water in such a way that there will be no side failures on the clay? Okay. Okay. So with that, then we can determine the height h in such a way that the effective stress is zero. Okay, because if the effective stress is zero, then uh, the stability of the saturated clay will already be lost, no? Because there's no particle to particle contact already. Okay, so what is that limiting height? So to do that, we can probably get now the total stress. Okay, we can get the total stress at point A. Here, sorry, the total stress at point A here. Okay, so to do that, you now have for the total stress, that's 7. The 7 minus 5 meters, that gives me 2 meters. Okay, multiply that by the saturated unit weight of clay, then plus. Okay, that's plus h. Okay, this is small h times the unit weight of water. Okay, that gives me the total stress at point A. Now for the pore water pressure, that's equal to 4.5 meters. Okay, this one here, that's the height, and it's a piezometric level of 4.5 meters. Then you can multiply this by the unit weight of water. That for the uh, that's for the pore water pressure. Okay. So for loss of stability, okay, for loss of stability, then the effective stress must be equal to zero. Okay, so that means the total stress minus the pore water pressure, which is equal to the effective stress, but the effective stress is already zero. So let's just try to substitute this one here for the total stress, and then this one here for the pore water pressure. Then we can now calculate this height h to be equal to 0.63 meters. Okay. So that means you can only have here as high as zero point 0.6 meters, no, of the total depth of 5 meters. That means if you pour water in such a way that the level here is already higher than zero point 0.6 meters, then yeah, the stability in the clay can be lost already, and failures can occur. So you can just imagine that if you have here a 5 meter depth, then you have the people working here where people is just around 1.8 meter height. Okay, and then you put water there above 0.6 meters, then it may not be good for safety, for example. Okay, okay, so I think this will be our last example. Yeah, okay, so our last example. So in this example, we are considering the upward flow of water through a layer of sand in a tank. Okay, as shown here. Okay, wherein you have the inflow here going up after you open the valve. Okay, then you have here a sand layer. Okay, and then you have here uh, um, a water level, a depth of water. Okay. So the depth of water is about zero point 0.7 meters deep. Okay, and then the thickness of the soil column is 2 meters. Okay, yeah, and then we have here 2 points A and B, where point A is about 1 meter below the top of the soil column, and then point B is about 2 meters from the top of the soil column. Okay, and then Okay, we inserted piezometers. Okay, we inserted piezometers here in such a way that, here, yeah, this is now the water level, and then here you have the water level. Okay, so I would expect the water level in the piezometer at point B to be higher than um, this level here. Okay, because the flow is going upwards. If the flow is going downwards, then this will be the opposite uh, heights. And this one will be higher, and then this one will be lower. Okay. Now, the difference between the two piezometric levels is about 1.5 meters. Okay, and then for the sand, you're given the following um, soil properties, wherein the void ratio is equal to 0.52, and the specific gravity of solids is about 2.67. Okay. So the problem is we are asked to calculate the total stress, the pore water pressure, and the effective stress at points A and B. That's for the first question. And then the second question is we are asked for the upward seepage force per unit volume of soil. Okay. So to answer letter A, okay, um, I think, I think we have here a saturated unit weight of sand, but the saturated unit weight is not given. But we are given other parameters such as the specific gravity and this void ratio. So we have here a relationship between the void ratio, the specific gravity, and the saturated unit weight. If you try to recall our first two, three lessons, okay, and then multiply that by the unit weight of water. So just simply substituting the given values, then we can calculate the saturated unit weight, um, which is equal to 20.59 kilonewtons per cubic meter. Okay. So to get the total stress at point A, so basically we have, let's see, that's a point 0.7 times the unit weight of water. Okay. Then that's plus 1 times the saturated unit weight of the sand. Okay, so that gives me this one here. Okay, then just simply substitute the values. Okay, this is the saturated unit weight and the dry unit weight. That gives you 27.46. Okay, now for the now before we go to the pool water pressure, okay, um, for the uh, point B, okay, for the point B, the total stress is equal to zero point 0.7 times the unit weight of water for this part here, plus 2, that's a 2 at point B, multiplied by the saturated unit weight of sand. So basically, it's just the same. You just replace 1 meter by 2 meters. Okay. Now, for the pool water pressure, okay, at points A and B. So then we have at point A, we have 1 plus zero point 0.7, okay, plus this, sorry, plus, yeah, plus this, yes, this height, this height, okay. It's not so clear, but yeah, this this height can be calculated by simply the hydraulic gradient, which is 1.5, okay, 1.5 over 2 multiplied by 1 meter by ratio and proportion, okay? Now, by the way, this 1.5 here is um, the height from this level down to the top of this water, not this one here, okay? Uh, the drawing is not so it's not that just clear. Okay, so basically, this level here is a little bit higher than this level in such a way that that will give you this one here, yeah? This height. Okay, so with that, we can multiply by the unit weight of water that gives us this value. Okay. Now for point B, so then you have for point B, the pore water pressure is now at point B, that's 2 meters plus zero point 0.7 plus 1.5 meters. Okay, so that gives you this total height. No? That gives you this total height. Kanina, that's um, that's 1 meter plus zero point 0.7 plus this small amount. That gives you this um, total height. No? Total height at point A. Okay. So multiply that by the unit weight of water will give me 41. Okay, zero point 0.2. So for the effective stress, then it's just the total stress minus the pore water pressure, which will give me 3.43 here. And this one, 48 minus 41 will give me this one here, 6.85. Okay. Now for part B, we are asked to determine the upward seepage force per unit volume. If we try to recall, um, the upward seepage force is per unit volume is equal to the hydraulic gradient, multiply that by the unit weight of water. But by definition, the hydraulic gradient I, okay, is equal to, yeah, the head, no? Is equal to the pressure head over the length of flow. Okay. So in this case, if this is the flow of water, the length of flow is 2 meters, and then the pressure head is 1.5 meters. No? Okay. Uh, so then the hydraulic gradient uh, is now 1.5 over 2. That gives me 0.75. Okay. So the hydraulic gradient, I just substituted here for the formula for the seepage force per unit volume. Okay. Then that gives me about 7.36 kilonewtons per cubic meter. Okay. So this is now the upward seepage force. Okay. Because here the direction is upward, but if the direction is downward, then this can be the downward seepage force per unit volume. Okay. So if you want to get the seepage force, then just multiply this amount by the volume of the soil, okay, to get the seepage force. Okay, so I think that's the last slide. Okay. Um, are there any questions or clarifications so far? Let me just stop share. Okay, so I hope I am clear with everyone. Again, I'm trying to be as slow as I can, so as not to confuse you with the terms between the total stress and then the effective stress. Okay, yes, there's a question here. With all the problems shown related to changing regional stress by finding a different um, groundwater level, by finding different groundwater level.